So for a warm-up to this lesson, we are going to look at these three triangles and use the Pythagorean theorem to find the missing side of the triangle. I'm actually just going to do this with one of them, and we'll talk about what the missing side of the other two triangles will be. So in the first triangle, because we are missing the hypotenuse, that is your side C. So we've got 3 squared plus 4 squared equals C squared. 3 squared is 9, plus 16 equals C squared, and so we have 25 equals C squared, square root both sides, so our missing side is 5. So sometimes when you guys do your Pythagorean theorem, you get these triangles where it just works out so nicely, and the third side is a whole number. It's not a radical that we have to reduce. So the next two examples are that same kind of triangle. This one, 3, 4, 5, if you notice, those numbers were doubled. We went from a 3 to a 6, a 5 to a 10. So what do we think this missing side down here is going to be? Well, it was 4 in the first triangle, so it's going to be an 8. Now, if you take that same 3, 4, 5 triangle and compare it to this one on the end, we can see we went from a 4 on the bottom to a 12. We went from a 5 to a 15. So we can tell that those numbers were all multiplied by 3. So you can take the original 3, multiply it by 3, and get our missing side of 9. So that leads us into something called a Pythagorean triple. So Pythagorean triples, any three whole numbers that satisfy the equation, and the equation that it satisfies is a squared plus b squared equals c squared. So the Pythagorean theorem will form a Pythagorean triple. So if all three sides are whole numbers and it works out in a squared plus b squared plus c squared, we call that a Pythagorean triple. So here are some examples of Pythagorean triples. These are from the last side. You got 3, 4, 5, 6, 8, 10, 9, 12, 15. So we already saw that multiples of any Pythagorean triple are also a Pythagorean triple. You know, we had before 3, 4, 5. We multiplied those numbers by 2, so 6, 8, 10 was also a Pythagorean triple. We multiplied them by 3, and we got 9, 12, and 15. Those are all Pythagorean triples. So here are some Pythagorean triples, and if you take any of these triples and multiply them by 2, 3, 4, your result will be another Pythagorean triple. So for example, the first one, if you took all those numbers and doubled them, you'd get 10, 24, and 26. That is also a Pythagorean triple. So just a side note, when we list off our Pythagorean triples, the first two numbers, these are always going to be the legs of the triangle, and then the last number is always the hypotenuse. Okay? So I think it makes sense to say there are infinitely many families of Pythagorean triples, but above are the ones that are used most frequently. So these are used quite frequently. The 3, 4, 5 is another frequent one. But you can always multiply by 2, by 3, by 5, by 100, and you get another Pythagorean triple, which is why there are an infinite number of them. All right, so knowing that Pythagorean triples exist, you can apply that to finding missing sides of right triangles. And this is called the principle of the reduced triangle. So, for example, this says to find x, we've got a right triangle, 24, 18, and x. And what we can try to do is reduce the triangle. So can 24 and 18 be divided by the same number? And think of the biggest number you can divide them by. 6 fits into both. So if you take 24 and you divide it by 6, you get 4. So I'm going to go ahead and put a 4 over there. If you take 18 and divide it by 6, you get 3. So what I'm noticing is here we have a 3, 4, and because it's a right triangle, I know that the last side has to be 5. So we've got a 3, 4, 5 triangle. Now, x does not equal 5 because 5 would be part of the reduced triangle, the 3, 4, 5. And what we did, see how we divided by 6 to get the reduced numbers? So if you're starting with the reduced number of 5, if you multiply it by 6, that's going to get you the value of x. So x equals 30. But we used the principle of a reduced triangle, the 3, 4, 5, to figure that out. So here are some steps written out. Reduce the difficulty of the problem by multiplying or dividing the 3 legs of the triangle by the same number. So that's when we divided by 6 up here. And we recognize it was a 3, 4, 5 triangle. Solve for the missing side, convert or reduce to the original triangle. All right, so here's another couple other ideas with this reduced triangle. So we've got this right triangle, and we can try to make the problem easier or reduce the difficulty of the problem by multiplying or dividing the 3 lengths into something by the same number so that we have a Pythagorean triple. So what we look at is the numbers we're given. So 24 and 10, can we divide those by the same number? And you might say, yeah, well, they both can be divided by 2. I think that's the biggest factor of both. So 24 divided by 2 is 12. So I'm going to go ahead and put a 12 over there. 10 divided by 2 is 5. And we're going to start to recognize we have a 5, 12, and then our missing side would be 13. 5, 12, 13 is a Pythagorean triple. So remember, 13 is not the answer for x. That's just the reduced triangle, 5, 12, 13. So to figure out what x is, all we have to do is take the 13 and multiply it by the 5. Not the 5, sorry, multiply it by the 2. Whatever you were dividing by, we're going to have to multiply by the 2 to get 26. So x is equal to 26. All right, this next example, we're going to have to end up using the Pythagorean theorem, and I'll explain that in a second. But first, take a look at the 2 sides you're given. We can reduce the triangle. So 18 square roots of 3 and 6, can they be divided by the same number? And they actually can both be divided by 6. So 18 square roots of 3 divided by 6, what you end up doing is dividing those numbers. 18 divided by 6 is 3, so you have a 3 square root of 3. That's the reduced number. If you take the 6 and divide it by 6, you get a 1. So that's a reduced number. Now, in the last couple examples, the reduced triangle was a Pythagorean triple. In this case, it's not. But what we can do is we can work with these smaller numbers in our Pythagorean theorem to help us get the answers. So sometimes it's just easier to work with smaller numbers. So that's what we're going to do. We are going to set up our Pythagorean theorem with those 2 legs. We're going to say 3 square root of 3 squared plus 1 squared equals x squared. 3 square root of 3 squared, remember square the 3, you get 9. The square root of 3 squared is 3, so this becomes a 27 plus 1 squared is 1 equals x squared. 27 plus 1 is 28 equals x squared. Square root both sides, and we get, we're going to have to reduce this. What perfect square number fits into 28? 4 fits in 7 times. So x is equal to 4 times the square root of 7. So here's where it just gets a little bit tricky. What we want to remember is that we just found the reduced side. The reduced is 2 square root of 7. I messed that up down there, didn't I? Let's see. Yep, be careful about that. The square root of 4 is a 2. So I'm going to make that a 2 right there. So 2 square roots of 7. All right. So to get our final answer, to get this side length right here, think about what did we divide by? We divided by 6 to get the reduced triangle. So once you get your answer, 2 times the square root of 7, if you multiply that by 6, that's going to get us the answer that we want. So when you multiply this, it's only 6 gets multiplied with just the like term. the 6 times 2, and we get 12 times the square root of 7. And that is our answer. So what we just did is we reduced the triangle, we did Pythagorean theorem with easier numbers, and when we got our answer, we just had to multiply it back up so that it matched the given sides that we had. And we will have more examples of this following this video.